So here is the apparatus. We have already described it. This is the plate from which the photoelectric effect will take place, and from the source L light is coming. This E is counter plate. This U is the plate from where we expect this photoelectric effect, and that is placed at certain potential that you can control from here. And then this is opposite plate, another metal plate, and potential of this can also be controlled from outside. So you can create a positive or negative potential difference, whatever you like here. Then this metal plate has a hole in front of this cathode, let me call it cathode, and then from here if something is going this way, straight it falls on this alpha. There is another plate alpha, metallic plate alpha, and this is connected to an electrometer. Electrometer is some kind of a simple device where charge falls on the electrometer plate, and how much charge is falling, that can be measured, right? That can be quantitatively measured. So in how much time, how much charge has been measured here, that tells me the kind of current received. Now this is another similar metal beta electrode, you can say, and this is connected to another electrometer. So this is the setup. Now when this light is put on, what is seen? Right? So if suppose this is at neutral potential, these two potentials are equal, or it is slightly more negative than this, then what will happen? What is seen in the experiment of Lenard? This is 1902 that this experiment is done and reported. So you have a kind of charge which is deposited here, and you can measure how much is that charge in how much time. So Lenard had studied that, and then if they put some coils here outside and create a magnetic field, those magnetic fields can deflect this beam. The beam which is coming, that can be deflected by putting some magnetic field here using coils or so, and the value of the field is adjusted so that this beam goes and falls on this beta. And there also you can measure how much charge is there, and you know that okay, whatever charge was coming here, now it is going there. So this beam, when this light is on, some kind of a charged beam comes out, and that charged beam normally goes straight, but using magnetic field you can deflect it. And how much magnetic field is needed to deflect it from going in this straight path reaching beta? Okay, so from that one can make calculations, and Lenard did all these calculations and found that the charge by mass ratio, if you consider this to have massive particles having mass, right, and charge of course, then this charge and mass ratio E by m, that can be calculated, and that matches with what J.J. Thomson had done for cathode rays since 1897. So it is established that this is same cathode rays. The ultraviolet light emits from this cathode or this metal plate the same kind of cathode rays which were generated when in the vacuum tube you have a cathode, anode, some 30,000 volts you apply and put some gas in that vacuum tube at appropriate pressure, and then create some negative charged beam. So that cathode ray beam and this beam are identical. That was established from this experiment. So that was one result. Now the other result was variation with this voltage. Variation with this voltage. Suppose it is going and falling here, and then you change the voltage. Okay, this is negative particles are coming in, and therefore if you put a negative voltage here as compared to this, with reference to U, if you put a negative voltage here, then this charge will be repelled, and if you increase that negative voltage in magnitude, then this repulsion will be stronger and stronger, and at a certain stage you find that alright, there is no current reaching here. The entire thing which is emitted from here is going back. Just like if you throw something up, and because of gravity it comes back. Similarly, from here the cathode rays are ejected, but then because of this negative plate here, they are forced back to go on this U and not reach here. So that was the kind of stopping potential. Okay. So again, if you consider in terms of mass and velocity, then the maximum kinetic energy of those particles will be equal to that E times that potential difference, and the same idea of stopping potential was there. So that maximum kinetic energy and therefore the maximum speed is related to that particular potential, negative potential, which stops all the current here. Right? Now, the observation is, the first observation that Lenard writes from his experiment is, one is this, of course, he establishes that this is the same as the cathode rays of J.J. Thomson, and then the next one is that only few volts of negative potential is sufficient to stop all the current here, and therefore whatever is ejected, that is ejected, the cathode rays are ejected with very small velocity. That is the conclusion. In the vacuum tube, in the normal vacuum tube, discharge tube, right, the voltages applied are some tens of thousands of volts, and therefore even if you make some aluminium window and take out those cathode rays will be high velocity cathode rays, because they had been accelerated by those tens of thousands of volts inside that chamber, and then these cathode rays are coming out. But here the cathode rays which are there, they are emitted with a very small velocity, and with the same velocity we can change only a little bit of it, right? So little bit of it. If you wish, you can put your potentials in appropriate fashion, and then the velocity can be adjusted according to your will. You can get slow cathode rays. Okay, slow cathode rays. If you don't apply any potential difference here, then whatever is ejected, that's with same velocity it will go. Of course, there will be complications of a charge being accumulated here, and that negative charge itself will start repelling the newcomers. So those things will be there, but nevertheless, you can accelerate with a whatever volt you want. 100 volt if you want 100 volt, yes. 50 volts, yes. 20 volts, yes. 1000 volts, yes. So in the normal cathode ray tube, the constraint is that whole thing fires only when you apply tens of thousands of volts. So you always get fast cathode rays. But here you can make a window here, aluminum window, and take out these cathode rays, and that could be slow cathode rays, and the velocities of those can be tuned by playing with this potential. So those are kind of advantages that Lenard talks about this. As far as the measurement goes, he has a most important observation quantitatively, that he changes the intensity of this UV light. He changes the intensity of this UV light, and to make that change in intensity is not very difficult. You just change the distance of this lamp, this source, from this window, and therefore from this cathode. So if you take it away, the intensity will be lowered. If you take it closer, the intensity will be more, and you can do all that inverse square thing and so on and so forth. So from the distance you can sort of compare intensities. What is the intensity now, and if I take this lamp here, what will be the intensity? So from the distances you can make those comparisons. So I can be varied, the intensity can be varied, and then he finds that the velocity of those cathode rays coming out, which is measured by this potential, the negative potential which is applied here, the negative potential which is enough to repel even the fastest part of that cathode ray. Okay, so that is the measure of the velocity with which these cathode rays are coming, at least that maximum velocity. And that he finds that this velocity, he talks in terms of velocity, nowadays we talk in terms of kinetic energy. So velocity of cathode rays, I am not writing electrons. Okay, so in fact Lenard uses the word quanta of electricity, right? Thomson uses the word corpuscles, he uses the word quanta, and finally the accepted word is electron. Alright, so velocity of these quanta is independent of intensity of UV. So this is a very, very important result, and that creates a lot of speculations, because this is 1902 and the wave theory was very well established. We will talk more about this wave theory and things related to light after this lecture perhaps. And but then the wave theory was very strongly was established there, and then this particular result was very, very surprising to Lenard. And Lenard interprets it in a very innovative fashion, which finally does not stand, but this interpretation was really nice. I liked it, and history says that that was accepted by the physics community for about a decade or so, right? And what was that? The mechanism, he thought, since it is independent of this intensity of light, even if I am putting more energy per unit time on this material, even then the electrons or the quanta are coming out, or the cathode ray is coming out with same velocity. Alright, so it concludes that the quanta are not receiving energy from the light at all. Okay, the mechanism of these quanta being liberated from the atom and the quanta are coming out. So in this process, the light is not giving its energy to the quanta. Quanta does not need the energy of the light, because if this light energy is transferred to the quanta to come out, then more intensity means more energy, and more energy means the quanta should come out with a larger energy. So since for all intensities, the quanta are coming out with the same velocity, this tells me that the quanta are coming out not by taking the energy of the light. The quanta themselves are having that energy as a part of that material, as a part of that atom. These quanta have some kind of energy. They are vibrating, or they are doing some kind of oscillations, and some energy is there. And different atoms and different quanta have different kinds of energy in its normal state in the metal, and the only thing is when light comes with sudden energy, and if that light, which is established as electromagnetic wave, it has oscillating electric field and magnetic field. So if that frequency of vibrations of electric field and magnetic field and frequency of vibration of those quanta inside that atom, if that matches, some kind of resonance takes place, and then the quanta start vibrating more violently, and then they are able to come out. But the energy is already there. The energy was already there. They were oscillating there with some energy. The light is only triggering those quanta with appropriate energy which are resonating with the light frequency to come out of this metal. So this was called triggering hypothesis. Okay, so because of that, the conclusion, very important conclusion that he derived, that these quanta are not taking energy from the UV light. They already have the energy, or they use their own energy in the atoms or molecules, and light only triggers them to escape. Okay, so this was the conclusion that Lenard draws from this observation. And another observation is that if you increase this voltage, finally it goes to a saturation current. So that is understandable, because once these quanta or electrons, which we call it today electrons, if they come out from here, and then if this potential is not high, then some of them will just make a charge here and they will stay here. Some will go in straight directions. But then if you do have some kind of positive potential, then it draws them. And if you have sufficiently high, then all the quanta which are emitted, if all of them go through this, not all of them, they are of course blocked here and there, but there is no side going in this side or that side and so on. So they are all streamed in a direction, so you get a maximum current, so that saturation current is there. So all that variation of I, variation of this current here as a function of this voltage, that also he knows that, okay, this kind of, so this kind of things is measured, this kind of things is measured, and then a lot of theory is developed from here. So that is all derived from this. Lenard does not quantitatively explores the dependence of this current on frequency, or this maximum velocity on frequency. So that was not on the agenda. Although he says that, okay, if you change the slab, material in the slab, that changes the characteristics, but that frequency relationship, or giving a monochromatic light of sudden frequency, those things were not part of this Lenard's experiment. Now, I should mention that in 1900, in that period when these experiments were done, Lenard was almost sure that these are not the normal particles. these are still, he thought that it's something like that ultraviolet radiation. So this is charged fine, there are quanta fine, it behaves like particles. It behaves like particles, but he had a conviction that these are essentially not material particles as such, but these are some kind of radiation. So that also I should mention, there's a lot of discussion and theory in his paper that we will not go into that at present.